Okay, we'll get started today. We're going to take a shift, and we're going to come back to Monte Carlo method. So I know we took a brief aside, getting into Bayesian statistics and Bayesian thinking, and we actually I posted a homework assignment last night, and that will be due on 1 week from Friday. So you got 9 days to do it. And that covers important sampling and some Bayesian concepts. Okay. Today we're going to cover kind of Markov chains. Okay. And the reason why we have to first talk about Markov chains and whatever is that what we are going for is we want a way to be able to sample from some target distribution. And we've already discussed, like the first 3 weeks of our course was just about sampling from some target distribution. And we talked about several ways to do that. Okay, so let me just get into the why. All right, so this is what we want. We want, basically, and the reason why we want to sample is we want to learn properties about some random variable, some random distribution. Okay, so we want to learn properties about a distribution. Okay, the distribution is too difficult for us to analyze analytically, so we are going to approximate it by getting a random sample. Okay, we want to learn properties about the distribution. Maybe the distribution is too complex for analysis, so instead we approximate the distribution with a random sample. Okay. With some of the approaches that we have now, this could lead to a very inefficient way of generating a random sample. Okay. Okay. So some of our methods, our current methods, can be very inefficient. Okay. Mathematically, as n goes to infinity, the distribution we have will approach the target distribution. That is mathematically true, but that's when we go to infinity, and we don't have time to go to infinity. Okay. So, we can leave the computer running for an hour, maybe even overnight, but that's still far from infinity. Okay. And often we will often have distributions that are very sparse. Okay, which means most is 0 or close to 0, and only only a small region has values. And so you can imagine if we do a normal distribution from say -25 to +25, okay, the normal distribution looks something like this, right? And if we were to do a random uniform sampling on such a thing, okay, if we were to do random uniform sampling, like if we did rejection sampling, and our proposal distribution was uniform, okay? And so first of all, it's not entirely accurate because the normal distribution has a support that goes from negative infinity to positive infinity, but we might say from negative 25 to positive 25, you know, outside of that, it's pretty much zero, we're gonna ignore it, okay? Fine, all right? So we can do, you know, random uniform sampling from minus 25 to positive 25 and do rejection sampling for everything that's outside of this, right? And what would happen if we did that? We would be rejecting like 99.9% of our values, and only a very, very small select few, maybe not 99.9, but with the 50 and only values between like 3 and -3, so 6 out of 50. So only like 12% of our values would probably be accepted, okay? So rejection sampling with a uniform proposal here would lead to, you know, kind of an acceptance rate of probably around 12% or less, not even, probably. It's hard to say, you know, less than 10%. Okay, I don't know. You'll have to figure that out. So what a Markov chain does is basically you do this kind of this random walk, and you end up, it's a more efficient way to kind of just stay in the region that is important, okay? But it's going to take a little while for us to get there, okay? So first we got to kind of talk about Markov chains and Markov properties, and we're going to start off with a kind of a discrete state Markov chain, and then we'll work our way up to the continuous case and the, you know, Metropolis Hastings algorithm and the Gibbs sampler and things of that nature, okay? This is a one-dimensional example. Our distributions are very sparse, usually in high dimensions. Okay, and I think I talked about kind of grid approximation and how when you go into high dimensions, you know, to do grid approximation, you need to start evaluating, you know, orders of magnitude, more and more and more points. Okay, so let's talk about a Markov chain. So let's start off with a two-state Markov chain. Okay. So a two-state Markov chain we have state A and we have state B. Okay? And we have a transition probability of going from state A to state B. Okay? So there are two possible states. Okay? And we have A and B, and we have a transition probability to go from A to B. Okay? And we also have a transition probability of going from B to A. Okay? And if you are currently at A and you don't go to B, what does that mean? That means you end up back at A. Okay? And if you are at B and you don't go to A, you end up back at B. Okay? We also have transition probabilities to go back to themselves. end up back at itself. Okay. And so, you know, we could say, so for example, we could have weather, and we can say A is sunny, and B is anything other than sunny. So we'll say not sunny, which includes cloudy, rain, etc. Okay? So either the weather is going to be sunny or it's not going to be sunny. And so, for example, the chain could go, you know, you have sunny weather, sunny weather, sunny weather, sunny weather, and then it becomes not sunny, and then it's not sunny for a few days, and then it goes back to sunny, and then maybe it goes back to being cloudy or rainy or whatever, and then it goes back to being sunny or something like that, okay? This is what weather in California could look like. And so we can ask, you know, if it's sunny today, what is the probability that it will be sunny tomorrow, okay? Now this is the defining property of a Markov process, is that tomorrow's probability, or tomorrow's state, the next state, depends only on the current state and nothing else in history, okay? So what happens tomorrow depends only on where we are today. It does not depend on anything that has happened before in the history of time, okay? This is the key important Markov property. Okay, we call this memoryless. And this means the next state depends only on today's state. Or actually, not today, but the current state. Okay. So we might say that, you know, in real life, weather is not Markov. It doesn't exhibit the Markov property, okay? Because, I don't know, you know, what happens in tomorrow's weather could depend on, you know, the weather that was several days before. But we could also say, you know, it's approximately Markov, and we can kind of treat it as if things only depend on the current state, okay? Okay, let me see. All right, so we could say we can create a transition matrix. And let me just consult my notes to make sure that when I'm talking about a transition matrix, because sometimes we write it's oriented a tiny bit differently. So whether okay, so we will have the transition matrix. We'll have the current state, A and B, and then the next state, A and B. Okay, and so we'll say if it is currently sunny, then the probability that the next day is sunny is going to be 0.7. And then if it's currently sunny, then it can also end up being not sunny the next day, and we'll say there's a 30% probability of that, okay? Over here we'll have 0.4 and 0.6. So that means if today is A, then probability tomorrow is A is equal to 0.7. It's basically what we have. Okay, and again, this reflects our okay, so I would put a 0.7 here, and then I would have a 0.3 over here, and from B to A, this is 0.4. Oh, I'm sorry, I have this backwards. A to A is 0.7, and A to B is 0.3. I apologize. Okay, and then B back to B is 0.6. Okay. We have there's a few key terms. Okay. One is known as irreducible. Okay, and chain is considered to be irreducible if I want to also say this is called ergodic. Yeah, irreducible, also called ergodic, meaning that a chain is irreducible or if you can reach all other states from any other state. Okay, so what this means is that if I start at A, it's possible to end up at B. Well, and there's only one other state, okay? And if I start at B, it's also possible to end up at A, okay? So this is irreducible. You know, you could have some kind of matrix, some kind of thing that looks like this. And maybe all of these go like this, right? So here's another one. Okay, and so if I start at A, can I reach E? Yes, it might, if these are low probabilities, okay, it might take me a while to reach E, okay, but I can, right? I just have to first go to B, then I have to go to C, then I have to go to D, then I have to go to E, okay? If I start at E, can I end up at D? Yes, okay, I have to start at E, then I go to A, then I go to B, then I go to C, then I go to D, okay? So this thing is ergodic, okay? Because from any state, I can reach any other state, okay? It might take me a while, right? And I might end up at other places many oftentimes, but it is possible to reach any other state, okay? What makes something not ergodic is if you have kind of basically a dead-end node, right? So if you end up with a node that says like, once you end up over here, you're stuck over here, then this is not ergodic, okay? Or, you know, and you could have like another matrix over here, but it's kind of like, or another network over here, but like once you end up over here, there's no way to get back, right? It's like you've crossed this threshold, and now that you're over here, you can't go back to the other states, okay? So this would be non-ergodic, including this, all right? So this part over here, if we didn't have this, would be irreducible in that you can reach all other states from any other state, okay? Over here, if we include this, this makes it non-ergodic, and I'm running out of space. So that's something that's ergodic. Okay. There's also something called aperiodic. Let me just copy this. Periodic versus aperiodic. Okay. Periodic means, so a kind of a Markov chain is periodic if you can if certain states are possible only at certain periods, or only at certain, I don't know, intervals. Intervals or periods. Let's see. All right, so let's say I have this. I think this would be aperiodic, all right? So, maybe not. Okay, so basically, well, we'll do this, because I know this for sure is aperiodic, and maybe the more complex one is not. I don't know. Okay, let's say this was your state diagram. Okay, in this case, the states will go A, B, A, B, A, B. Okay, because you can't go back to yourself. So it's going to go from A, it's going to go to B, A to B, so on and so forth. Okay, which means A can only show up on the kind of the even cycles, and A only shows up on the odd cycles, and B only shows up on the even ones. Okay, so this one is periodic. Okay, certain states are only possible at certain times. Okay, so that makes it periodic. Okay, aperiodic means that once the chain has been running, okay, a certain state can appear, at any time, right? It's not limited to just certain periods. That basically it can show up whenever. Okay, so aperiodic is just the opposite. Okay, states can appear whenever, right? I'll just say whenever. Now, of course, certain states might be impossible. Like based on your current state, it might be impossible for the next state to be a particular state, but just given some arbitrary starting point, at some point in the future, it can be whenever. Okay, at a practical level, if your network has a node that goes back to itself, then it will become aperiodic. Okay, so here I've got A and B, and let's say it goes like this. And if you have one node that can go back to itself, it will make the thing aperiodic. At least one node. Okay, so if it's possible for a state to end up back at itself on the next cycle, then it will be aperiodic. Because over here it had to go A, B, A, B, but now I can go A, B, B, A, B, and then now the, so, you know, whenever I'm at B, I have to go to A next, but you know, it's possible. Okay, so if I go A, B, or A, B, then, you know, we can see that the A's or the B's can end up either on the even or the odd cycles. Okay, so there's no periods if a thing can go back on itself, or if the next state can be the same state that you're currently at. Okay. So let's go back to kind of this thing. We have state A and we have state B. And here's my transition matrix. So this is kind of current, and this over here would be our next. Okay, and I forget, what were the numbers? I said A to A would be 0.7, and this would be 0.3, and B to A is 0.4, and this is 0.6. Is that what I said? Okay, so we'll call this transition matrix. This is a transition matrix P, okay? So we will let this be transition matrix P. And there's something called a stationary distribution. Okay, the stationary distribution is basically when the system is at equilibrium. Okay, it's the distribution of the system at equilibrium. Okay, so when it's not at equilibrium, basically you would find out where everything is in the next state by taking your current state and multiplying it by the transition matrix. Okay, so when you are, or just, well, anyway, it's not just when you're not at equilibrium, but you can just find out, so let's say the current distribution is 100% is at state A. Okay, which means 0% is at B. I'm going to write 1 to 0 for A and B. And then I've got my transition matrix P, 0.7, 0.4, 0.3, 0.6. Okay, I'm going to multiply this, and this again, this is A, B. Okay, and when I multiply these two together, what will I get? This will tell me, I'm going to get so I'm multiplying a 1 by 2 by a 2 by 2, so I'm going to end up with a 1 by 2, and this will tell me how much I have at A and how much I have at B, right? So I go 1 times 0.7, plus 0 times 0.4, I'm going to have 0.7 here. And I do 1 times 0.3 plus 0 times 0.6. I end up with 0.3 right there. Okay. So if 100% of people start at state A, and we undergo this transition matrix, okay, it makes sense that after one iteration, after one phase, 70% will end up at, keep drawing this backwards, 70% end up back at A, and 30% have transitioned to B. Is that okay? And then, all right, let's say at the next iteration, if I want to know where do we end up, so I've got A and B, and I've got the same transition matrix, 0.3, 0.4, 0.6, okay? I want to know how many end up back at A, okay? So I would do 0.7 times 0.7, I get 0.49 plus 0.7 times 0.3 times 0.4, so we have 0.12, so that gives me 0.61, and then if, you know, the math should be correct, but I do 0.7 times 0.3, and I have 0.21, and 0.3 times 0.6, 0.18, and over here I get 0.39. Is that okay? So at the next phase, I've got 70% are at A, and of that 70%, 49% end up back at A, okay? I also have 30% at B, and of that 30% at B, 40% of them, so 12% of the total, end up back at A, for a total of 61% are now at A, okay? And then at B, you know, we have 30%, and of the people at B, 60% will end up back at B, so that's 18% of the total. And then the ones who also end up at B are the ones who started off at A, and that's 70%, and of those, 30% end up at B. And so we have 21 plus 18 for a total of 39% will end up at B after 2 states. Okay? So is this all right? And we can continue applying this, and we can say, all right, what's the probability of people ending up here and there after you know, 10 iterations of our, you know, kind of our Markov chain, okay? Okay, oh, let me close our attendance poll. Okay, and all right, but I want to talk about the stationary distribution, okay? Okay, the stationary distribution, we often call this pi, and what happens is that when you take pi and you multiply it by the matrix P, so if you take the stationary distribution times the transition matrix, you end up with the stationary distribution, okay? We are now at a state of equilibrium, where basically the amount of people transitioning from A to B is equal to the amount of people transitioning from B back to A. All right? Yes?
Is pi scalar or matrix?
Pi is going to be a matrix, or a vector, representing the distribution across the different states. Okay? So pi is a vector, or basically a one-row matrix representing the distribution across the states, okay? So basically, what was I forgot. I keep forgetting my transition matrix. My transition matrix P was what? 0.7, 0.3, 0.4, and 0.6, I think. Okay. Okay, and so basically, the transition matrix here would be if 4/7 of the population are at A, and 3/7 of the population are at B, we will end up with a stationary distribution. Okay, and this is where basically we have A and B. So even though we have these transition probabilities, the number, okay, the number of those going from A to B is equal to the number going from B to A. All right, so if I do this, I have 4/7 times 0.7. So I have 4 times 0.7, 4/7 times 7, plus 4/7. Oh, I'm sorry, I have this backwards. It needs to be A will have 3/7 and B. No, I'm right. Okay. 4/7 times 0.7 ended up back at there, and why am I having trouble? Oh, 3/7 times 0.4. Okay. So 4/7 times. So what is that? 0.28 plus 0.12. So 0.28 plus 0.12 over 7, and this ends up being or 2.8 plus 1.2. Sorry, 2.8 plus 1.2. Can't do math. Okay, and that ends up being 4/7. And then the second one will be 3/7 times 0.3 plus 3/7 times 0.6. Okay, and that gives me 0.9 plus. No, 3/7 times, I'm sorry, 4/7 times 0.3. Gosh, this is hard. Okay, sorry, 4/7 times 0.3 and 3/7 times 0.6. It's like fractions. What is this fractions nonsense, right? Okay, so I have 1.2 plus 1.8, 1.2 plus 1.8 over 7. And that gives me 3/7. Okay, so when you take the stationary distribution, if 4/7 of the population is at A and 3/7 of the population is at B, and then you apply the transition matrix there, the next state ends up being exactly the same as the current state. Okay, so at this point, yeah, the individual pieces might be moving around, but the distribution remains stationary from one state to the next state, okay, or from one iteration to the next. Okay, so that's the stationary distribution. Okay, what's all this about? Well, we are going to set up an algorithm, I guess on Friday, where the stationary distribution, given if we come up with certain rules for the transition matrix, we can set it up in such a way that the stationary distribution will end up looking like the target probability distribution that we want. Okay, which means we can start at any state, and then we apply the transition matrix over and over and over again. Oh, and I forgot to say this, is that if it's ergodic and periodic, aperiodic, then eventually, as you apply the transition matrix, as that approaches infinity, it will approach the stationary distribution. That's an important thing I forgot to say. Okay, so so if your your Markov chain is ergodic or irreducible and aperiodic, then no matter what state you start in, no matter the initial distribution, okay, if you repeatedly apply the transition matrix, you will get something, or you will converge, not get something, you will converge to the stationary distribution. Okay. So basically, you have some initial distribution, and then if you multiply it times p, basically raised to the n as n goes to infinity, then this will approach the stationary distribution. Let me just kind of illustrate. We got 1 minute. Now I'll just show this very, very quickly in R, okay? Oh, come on, R. Start up for me. Okay, so I'm gonna just start off with, we'll call this state, will be a single row matrix with 100% 0, number of rows equals 1. Okay, so this is what state looks like. All right, and then P is going to be a matrix, so I'm going to R bind, what do I have, 0.7 comma 0.3, and the second one was 0.4 comma 0.6. Okay, so if I print P, it looks like that, okay? And then I do state times P, and so when we started off at 0.1, or with 100% and apply the probability matrix, we ended up with 0.7 times 0.3, okay? So let me do, I'll call this state and do this, and I'm just gonna repeat the same operation over and over again, okay? So I'm going to take the state, multiply it by P, and then store it back in state, and then and by putting parentheses around it, it asks R to print it out, okay? So I apply it again. Wait, oh, okay, wait, sorry. So we do this, and then and this is the calculation we got, right? After, if we start off with 0.7 and 0.3, and we apply the probability matrix, we get 0.61 and 0.39, okay? And then let me just keep going. And as we do this over and over again, you see we start to reach almost equilibrium, where the numbers change very little. It goes, if we look at kind of the values that we've seen, so we go from 0.572 to 571, 5715, 574, 56, over and over, and now it's getting close, all of these things. The transition matrix has kind of reached equilibrium here. Right? At this point, it no longer changes. And if we ask, well, what does this thing look like? Well, if I do state times 7, then we're at basically 4/7 and 3/7. Okay, so we started off at distribution of 100% in one location, and then we applied the transition matrix, and we got this and this and this. Okay, if I started off the other way, and I know I've run out of time, but let's say this is my state, okay, where 100% are at B. So then after one iteration, we're at 0.4, 0.6, okay, and I'm going to just keep applying. From 0.4 to 0.6, we go to 0.52 to 0.48, and then we keep applying this, and then you can see it starts to again reach kind of our state of equilibrium here. And at this point, it no longer changes. And again, if I take my state, we can see that it's equal to 4/7 and 3/7. Okay, and this is just a simple two-state property. Okay, two-state example. But we're eventually going to go for basically more states, and finally in like an infinite continuous case where we're going to go for that. Okay, anyway, this is kind of your very, very early intro to kind of Markov chains and whatnot. All right, we'll see you guys on Friday.
So why does the state when